So hello everyone, welcome back to another particular lecture series of our organic spectroscopy course. And this is the class 3 of our IR spectroscopy. So in this particular lecture, we are talking about the physical interpretation of IR, that is Hooke's law and bands in IR. So just simply recapitulate that what we have learned in our previous lecture. So in our previous lecture, we are talking about the IR spectroscopy and the selection rule for the IR spectroscopy, and we are talking about the different modes of vibration some kind of vibration, a stretching vibration and bending vibration. In the stretching vibration, there is a two type of stretching vibration is there. One is the symmetric stretching, one is the asymmetric stretching. And in bending, there is a two type of bending is there. One is the in plane bending, one is the out of plane bending. Okay, so I hope that thing will be clear for you. Now here in this particular lecture, we are little bit deep down to the quantum mechanics first, and then we again rank our IR part. Okay, so first let us understand the quantum mechanics behind the IR. So as I already discussed in our class 1, that in our system there is a different energy states are there, and between the two energy state there is a n number of vibrational energy state present, and between the two vibrational energy state there is a n number of rotational bands is present. Okay, now depending upon the strength of electromagnetic radiation, the transition has been observed. So in the case of IR spectroscopy, the infrared radiation have the energy which actually do the vibrational transition. Like if your molecule is something here, then after irradiating by the particular electromagnetic radiation in the IR spectrum, it will jump from V0 to V1 or V0 to V2. That's a completely different thing. But what happened that the transition has been observed, that means the vibration of the bond has been changed. Now let us understand this particular thing in a simple diagram here. So here you can see it is a, we can say it is a diatomic molecule. Okay, and this spring is denotes the bond. Now what happened that in the case of normal circumstances, the bond is elongated and vibrated in the ground state energy state of any kind of vibrational energy state. Now here in this particular figure, these all are not E0, that is called V0. And this particular diagram, this particular system is actually observed in the SHO model of simple harmonic oscillator model. So it suggests that even the every energy state it will looks like this type of thing. Actually not this type of thing. This is show the Morse potential curve, and this particular well contains different vibrational state. Now what happened that these are the diatomic molecule. Now this diatomic molecule in ground state it will be stretched and elongated and squeezed. So this thing already happened to generate this particular V0 vibrational state. Now, as the molecule is getting energy from the infrared region electromagnetic radiation, you can see there the elongation and the compression amplitude is increasing, and that's actually denotes the second vibrational state. And due to this particular IR energy, it that can be absorbed by this particular diatomic molecule and shifting the vibrational change to this area, and now this is called the transition. Now the transition occur from the ground state vibrational state to excited state of any kind of vibrational state. So depending upon the stretching and bending, basically the vibrational energy is observed. Now if the IR radiation or any kind of electromagnetic radiation have so much energy that the stretching will be much huge, so that the bonds getting breaks, and this area is called the bond dissociation energy. Okay, so in the IR region, electromagnetic radiation, it's capable to increase the amplitude of elongation and compression, and thus we got this type of transition. So this is the basic principle of the IR spectroscopy. Now let us talk about the Hooke's law. Now, if we know about physics Hooke's law, then it is also same about the spring kind of thing. So what happened that here, this particular bond is looking like a spring, and that's why this particular diatomic molecule has been treated as a spring type of molecule, and that's why the Hooke's law is very important. Now Hooke's law states that the force required to stretch or compress a spring is directly proportional to the displacement, that is F equal to minus kx, and the minus signifies the elongation and compression. Okay, now for the IR spectroscopy also we can say that the bond is nothing but a spring, and that's why the IR spectroscopy, the law is applied for bond vibration between atoms where the bond acts like a spring. Now the vibrational frequency of the bond can be derived from the Hooke's law, and it is given by something like this, that is nu equal to 1 by 2 pi root over k by mu, or nu bar, it is 1 by 2 pi c root over k by nu, where nu is the vibrational frequency and nu bar is the wave number. This is nu bar. K, K is the force constant of the bond, which actually relates to the bond strength, and the mu is the reduced mass of the two atoms involved in the bond. Okay, so we'll discuss about this later, but first let us see a IR spectrum first. So this is the example of IR spectrum, and this is spectrum that I generated during my master project work. So during my master project, I have synthesized one compound, and this is the IR spectrum of that particular compound. Okay, so here you can, if you look about this particular graph, then you can see that the peaks are inverted, first observation, and the second observation is there is a noise is there, like here is noise and here we can see some kind of noise. So there is a two question associated with the spectrum. So the first question is why the curve is inverted. Now if we look about here, that the curve is not absorption versus wave number, this is called transmittance versus wave number, and the IR curve is plotted between transmittance versus wave number, which instead of absorption versus wave number, and that's why the curve is seems like inverted. Now here in this particular curve, the top part suggested that 100% transmittance observed. Whenever the functional group absorbs some kind of IR spectrum, the transmittance goes down and we got the particular peak. Okay, and the second question is why there is a noise observed in spectrum. Like a molecule have different mode of vibration that I already discussed. Like a molecule contains a stretching mode of vibration, bending mode of vibration, and in bending there is a different bending, in plane bending, out of plane bending is there. So what happened that due to the different mode of vibration, this actually sometime actually overlap in the spectrum, and that's actually generates the particular noise. So I hope that this thing will be clear. Now let us talk about the different band in IR spectroscopy. Now depending upon the energy of the IR electromagnetic radiation, so what happened, it will show different jump. Like it will directly go to V0, that is the ground state vibrational state, to first excited vibrational state. Now if any kind of bond is go from V0, that is the ground state of vibrational state, to first excited state, then it is called a fundamental band. However, there is some time happen where the IR are strong enough to actually show the transition from V0 to V2 state, that is the second excited state. Then this type of transition is called overtone. Like here it is written that fundamental band observed due to the transition of V0 to V1, whereas the overtone that is observed between the transition of V0 to V2. And not only that, sometimes these two bands, fundamental band and overtone, are actually combined to each other to generate different sub bands. Sub bands are called that combination band, difference band, and the Fermi resonance band. So we'll discuss in the next slide. So here you can see that when the two fundamental bands are actually combined, then it shows the combination band or different band. Like here, if the both same phase band are actually combined, then the reinforcement takes place and amplitude of the wave is increasing, and then it is called the combination band. And if the both are in the anti-phase relationship and they are combining, their amplitude is decreasing, and this is called the difference band. Now when the fundamental band or overtone are actually combined, then Fermi resonance takes place. Now again we move to our IR region or IR spectrum, and you can see that here this is 1500 to 3500 around. This particular area is called the functional group region, and here mostly stretching bands dominate. Like the bands associated with the stretching mode of vibration is actually shows here. However, here in this particular C, if you see that 500 to 1500 area, and you can find that this particular area is certain mesh. because this is called the fingerprint region, and here stretching band is also present, as well as different bending band is also present, and that's why this particular spectrum area is looks like a little haphazard, and this is called the fingerprint region. So with this we have to end this particular lecture. In this particular lecture we are actually discussing about the quantum mechanics associated with IR spectrum. We learn about the IR spectrum and Hooke's law. So in the next class we will talking about the different fundamental vibrational mode and important IR peaks. So thank you for listening.